Hello fellow problem solvers. So today I'm going to be talking about how a sheep that I met in 6th grade helped me get to my first ever International Math Olympiad. Let me explain. So how you get to the International Math Olympiad is really country specific. Every country has their own rules and regulations for how they choose their team. In my country there is a final round, the team selection test, which is composed of 2 days of exams, sort of like the International Math Olympiad. And on the first day, I did the first 2 problems. And now I knew coming into the second day that I need to really solve 2 problems to sort of guarantee that I would be able to pass to the International Math Olympiad. So the fourth problem in the exam, so problem 1 of day 2, was a algebraic combinatorics problem, which was okay. I saw that I could solve it. But the problem number 5 was a combinatorics, and I knew that if I solve that problem, I'm getting to the IMO, and if I don't, it's going to be a really, really tough time. I knew that at the exam. So what was the problem? Well, the problem was so what you have is a natural number that's given to you, and then a set of weights, okay, such that every weight weighs 1 through n, where n is a natural number. Every natural number from 1 to n, we have a weight that is of that size, and that the sum of all the weights is even. So we could say have a set with a weight of weight 1, and another weight of weight 1, another weight of weight 2, perhaps, maybe 3 weights of weight 3, say that n is equal to, I don't know, let's say 4. And actually I need another weight here, and then say a weight of weight 4. And now I need to show, okay, their sum is even, that's why I need another 3. And I need to show that I can, put them into 2 subsets with an equal number of weights. I need to show that no matter what our n is and no matter what weights I have, I can do this as long as the 3 conditions are satisfied. So the first sort of idea that you get when you're trying to solve this problem is, say that you have a couple of weights that are of the same size. Say you have 10 weights, some sets, of weights, and you have 10 weights which are weight free. Well, I can think of that as me having 2 weights of weight free. Why? Well, I still have the same problem, right? I still am solving a problem, but I just have less degrees of freedom. And if I had 3 weights of weight free, I can assume I have 1. Because mind you, there's a problem where I have 1 weight of weight free, and I have the same other weights, the same configuration of the other weights. So I might as well assume I have 1 weight of weight free instead of me having a lot more degrees of freedom, and I have to solve this smaller problem to be able to solve the bigger one, right? So I might as well say that I'm in my worst case scenario with the degrees of freedom. So I can really just assume I only have 1 weight or 2 of each, 1 or 2 of each weight, really. And with that, I get back to my drawing board and I'm thinking about, okay, can I just do this inductively? That is the main thing. After you do what do you do when you don't know how to solve a problem? You play with the problem. So say what we're doing here for 4. What I do here, okay, I'm going to ignore the 4 frees. I'll just assume I have 2. In other words, I'll take 1 in set A, this one will be in set B. So I'll have, okay, the 2 frees, but I don't really care about those. And now let's put a situation, okay, 4 free free. Well, let me first try sorting the 1s, and then I have a 2. Okay, I'll sort the 1, 1, and the 2 here. Now, the 2 frees, I can do a free here, a free here. And now, if I have a 4, what do I do? Well, I can put, so they're equal now. So if I put the 4 in 1, this will increase this one by, they're now both, say, s. So then it will increase by s plus 4, but then the total sum is no longer 2s, now it is 2s plus 4, so I need to have s plus 2 in both sides. So if I put 4 here, and then take the 2 over here, now I have s plus 2 on both sides. I have a 7 here and a 7 here. And so I'm able to solve the problem, and I'm thinking of how can I build this up? And the natural idea is, okay, for n equals, if n is 1, I just have, 1 here, I'm done. If n is 2, my only possibility is, again, I have 1, 1, and a 2, or 1, 1, and a 2, 2. So if it's 1, 1, 2, 2, I put a 1, 1, a 2, 2. If it's 1, 1, 2, I have a 1 here, a 1 here, and a 2 here. And then if I have a 3, I can have a 1, 2, 2, 3, or 1, 2, 3. If I have a 1, 2, 2, 3, I'm going to do 1, 3, 2, and 2. And if I have here, I'll be 1, 2, and I'll do a 3 here. Okay, so I'm playing around with some small cases, and I'm getting a sense, wait a second, under which conditions can I really, just finish up inductively? And for me, while I was solving this, I was thinking of, okay, 4 and 6 really helped drill down for me. What was it that I needed to finish inductively? And here's where the problem takes a turn, because what I realize is that, and what happens is, say for 5, think about my 5. If I have 2 5s here, then if I have 2 weights of weight 5, then I know I can really apply my inductive sort of hypothesis on the weights 1 through 4. Right? If this is for n equals 4, the inductive hypothesis, the sum of all the weights is even. That's the only thing that matters, and I have 1 weight of each. Now, that's if I have 2, then I can, apply the inductive hypothesis there. I've put them into 2 sets, put a 5 here, put a 5 there. Now the trouble is that I can do the same really no matter what the n. If I have an n and n, I have numbers from 1 till n minus 1, weights here, either 1 or 2 of each. And I can just apply the inductive hypothesis here, and then bam, sets A and B are of the same size. I put an n here, put an n here, again, I'm done. And now the question is, okay, what happens if I don't have 2 of the biggest one, if I just have 1? Well, if this one is actually even, so if the number is 2 times some k, say 2 times k and 2 times k minus 1, the sum of this weight with all the other ones is even. So when I take this one out, I am left with a sum of weights that are even, 1 or 2, at least 1 of each of the weights 1 through 2k minus 1. Their sum is even, and every weight here is one of those. So again, I can apply the inductive hypothesis. And now what do? Well, I'll have 2 sets, A and B, and they'll have a sum of s, right? An s here and an s here. This is going to be some set here with a total sum of s, right, in both of them. So what am I going to do? Well, what did I do with a 4, really? This is where the idea comes in. Okay, I have 2 times k, so now the total sum is 2s without the 2k. When I add the 2k, it will be 2s plus 2k. So I need each set, after I add this one in, to have the sum s plus k. What do? Well, if the k is in set B, I'm just going to move it to set A, and now I've changed the sums. Now this new A has the sum s plus k, and B has s minus k. And what do I do with a 2k? Well, bam, I move it here, and now this is s plus k as well. So that's what we do in this case. Now, how do we deal with a case where we only have one weight that is an odd number? And this is where my sheep comes in, because I'm realizing, wait a second, if I have, 2k plus 1, and if I had, 2 weights that were of weight 1, I could take this weight and 2k plus 1, put them on the side, apply the inductive hypothesis, right? And then get, again, a situation where I have A and B, and they are both of sizes s. They both have s as their sum. And I have my weights of 1 and of 2k plus 1 on the side. So what happens when I add both of them? Well, the total sum here is going to be, after that, is going to be 2s plus 2 times k plus 1, right? 2k plus 1 plus 1, 2k plus 2, in other words, 2 times k plus 1. So what will happen? Okay, I will locate, let's say k plus 1 is here. Like each of the sets, like we did previously, will have the sum s plus k plus 1. So I take the k plus 1 from B, move it here. I take the 1 and the 2k plus 1 and move it into B. And with that, I have equalized these sets. Now, what happens if I don't have two weights of size 1? Well, then I can't really do this, right? Because I'm not really applying the inductive hypothesis there. And here I'm only able to apply it because I had two weights of size 1 that weight 1. But if I only had one, and if I took it away, I wouldn't be able to apply the inductive hypothesis. So what do I do? And this is the moment of the exam where I'm really, really trying to think, wait, how can I resolve this? This is the one thing I need to resolve, the one thing. And this is the thing that's, between me and the International Math Olympiad. It's the thing that I need to solve to get there. And what do I do? What is going through my mind here? And the answer is in here. And to explain this to you, this is a book that I got as a kid. And it's a book of riddles, puzzles, and enigmas. And this was such a cool book to me when I was a middle schooler, just going through it, thinking about all these different riddles. And it had things which weren't really riddles per se, but more maybe optical illusions. Why is this happening? And such a brain teaser filled book. And I just loved it because some things would just blow your mind. You think you have it, and then in reality, no, it has a different answer. And the riddle I came across here, which absolutely blew my mind when I saw it, here it is. It is the sheep riddle. And this is where I met that sheep, which helped me get to the IMO. So, let me read this to you. An old shepherd declares to his wife, "When I die, I want our eldest son to receive half my sheep, our middle son to receive a third, and our youngest son a ninth." At the moment of his passing, the shepherd had 17 sheep. After racking their brains, his three sons failed to see any way to respect the will of their father without carving up the sheep. Eventually, another old shepherd, a friend of their father, finds the solution to their problem. What does he propose? Think of this brain riddle for a second there. And what he proposes is the following. He says, okay, listen, we don't want to carve up the sheep, right? So let's do a little thing. I'll help you out. I will lend you one sheep, okay? And it says, wait, but we have 17, no, it's okay. No. I'm going to lend you one sheep. And now divide them up. And when they do, the oldest one gets what? A half. So that is 9 sheep. The second one gets a third, that is 18 divided by 3, that is 6. And now the youngest one gets a ninth, which is 18 divided by 9, which is a 2. So in total they've divided amongst themselves 9 plus 6, that is 15, plus 2 is 17. And there's that one extra sheep. What do we do? Oh, the old farmer then gets back his sheep. And mind you, when I saw this, I was absolutely mind blown. Like, what? How does that? Wait, he just resolved it, just gave them a sheep, and then he got it back, he just borrowed them a sheep, they resolved this math riddle, and then he got back his sheep, like, whoa! And to me, when I first read that, it stuck. And when I was in that exam room, maybe there was a little inkling of that idea that just propped into my mind. And I used it to solve this problem over here. Can you figure out how? Well, the answer is, and you should not feel bad if you cannot come up with this answer, for me, this was my eureka moment in all of my math competition exams that I ever took. This was my proudest, best moment. It's better than me winning the bronze, honestly. And the idea here that came to mind was this. Okay, wait a second. So what I'm really here doing is I only have one weight of weight 1. If I only had an extra 1 that I could, have on the side, I might be able to, resolve the problem. But if I have 1, then I don't have the sum of all of them be even. So what if I borrowed 2 more weights of weight 1? Right? Say I only have 1 weight of weight 1. I'll borrow 2 more. And I'll borrow them from the person who created the problem. Yeah, I know it's a little bit, that's how I wrote it down in my solution. And now, the sum of everything here is even. Each weight appears at least once. And now if I just put the weights of weight 1 and 2k plus 1 off to the side, apply the inductive hypothesis here, I'll get what? I'll get 2 sets, A and B, and they'll both have a sum of s, right? And then what do? Okay, one of them has k plus 1, say it's B. I move it from k plus 1 to A. Now this one has s minus, and this one has s plus k plus 1. And I take the 1 and the 2k plus 1 and put them into B, right? So now I have that. B has 1 and 2k plus 1, and A has k plus 1, right? And now they both have a sum of s plus k plus 1. Now my question for you, under which conditions am I really done? Like, what do I need to do to finish up? Well, I've borrowed these 2 weights and I need to, give them back. Same inspiration as the farmer and the sheep. And so if both weights, if there's a weight of weight 1 in A, then I can know, if this is the case, there's a weight of 1 in A, I can take the 1 from A, take the 1 from B, take them out, give them back to the person who created the problem, and then I've resolved my induction. Right? Problem solved. QED. But what if that isn't the case? What happens then? This might be a good place to pause, because what happens then is, okay, that means there's no weights of weight 1 in A. That means all the weights of weight 1 are in B. Okay. Well, what can we do in this case? Well, we look at, okay, let's see, weights of weights 2. What if there's a weight of size 2 in A? Well, I'll take the 2 1s that are in B, move them here, move the 2 1 over here. The sum remains the same. I've just moved 2 here and a 2 here, right, in total. And then I take a weight of size 1 here, a weight from size 1 here, and give it back to the person who created the problem, who I called in my proof the chef. So let's say, okay, what if there isn't any weight of size 2? What if all the weights of size 2, and then there's at least 1, is in B, or are in B? Well, then we go to free. And let's say that the smallest weight that's in A is greater than or equal to 1, and it's of size L. Well, by the minimality, there's at least another weight of size L minus 1 that is in B. L minus 1 being greater than or equal to 1. So I can take the L minus 1 from here, take the 1, move them into A, take the L, move it into B, and then take the 1 from A, take the 1 from B, give it back, and I'm done with my induction hypothesis. And that solves the problem right there. This problem, mind you, has a bunch of different solutions, had at least 6 or so. The person who suggested this problem for the competition thought this solution was the most greater one. And I find incredible pride in this solution. Now, you can find other ways to solve it. There are at least 5 that I know of that are different than this. 4 that I definitely can regurgitate that are different from this. Maybe there are even 5. I'm curious how many you can find down in the comments below. And what this shows is really that these riddles you sometimes see, puzzles, they seem kind of artificial and perhaps even unapplicable to life or anything else. And maybe, it's just a fun pastime doing problems like that, doing these riddles. But sometimes when you find that little thing in a riddle that just blows your mind and you remember it, you remember the way it blew your mind, it sticks. And then years later, literally, you can find it in the places you least expected. And the second case here is on really passion. Or not really passion as much as allowing yourself to feel awe or excited or wowed by a solution. I saw the solution to the sheep problem and I thought to myself, whoa, this is so cool. Oh my God, this is so cool. He just gave the sheep and then he did that. Now, of course, you might say, well, a ninth plus a half plus a third is 17 over 18. Of course he could do that. Like, come on, how didn't you see that? Well, and you could go like mathematically, well, the sons really didn't get a fair deal. Like one son got a bit more than he needed, so I don't know how much you really want to praise the farmer. It's like the youngest son got the best deal, okay? So really the oldest, the friend of the farmer who died was really, just like looking out for a little boy. He should have gotten, 1 point something sheep, but he actually got a whole 2 sheep. So who did he really help? Right? You can go ahead, make all sorts of arguments, but I think there's beauty that you can find when you're seeing math problems. And if you allow yourself to feel that beauty and be inspired by it, be wowed by it, it can stick. And the best way to really get better in solving math problems is to allow yourself to be wowed by a solution, to be wowed by an idea. Because when you're wowed by an idea, when you say, wow, how could you, that was so creative. And you're trying to think, okay, could I apply this elsewhere? Is this an idea that's applicable in other places? Or maybe not even that, maybe just allow yourself to be wowed. That same inspiration might come to you at a place you least expect it to. And I certainly did not expect, walking into that exam hall, that I'd use something I saw, a sheep I met in 6th grade. This finishes up our problem. And as always, thanks for problem solving.